Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi. Today we will continue our next lecture, which is part B of chapter 6, which is phase transformation. Okay, previously I already finished part A. So today I will make a recap about this part A. Okay, we already look at the definition of a basic concept, which is phase boundary, homogeneous. Then we have solution, solid solution. Okay, and then we have solubility limit, weight percent. Okay, this one weight percent is mainly we will see in the phase diagram, so that you need to understand this. Okay, for the weight diagram, weight percent is basically refer to the percentage of composition. Okay, in this case, we have brass consists of 70%, 30% of copper and zinc respectively. So in this case, if we look for the weight, indicates that if we have 100 gram of brass, we have for the weight supposed to be copper in 70 gram, and the rest is 30 gram for zinc. And then we convert to percentage to be 70 and 30% of copper and zinc respectively. So after this, we will see the in phase diagram, the composition on the x-axis. Okay, we have the temperature versus composition, whereby the composition at x-axis varies according to the increasing of foreign element. In this case, if we look at this diagram of copper, zinc copper or something, or we have the lead tin phase diagram, which is the tin will increase in percent starting from 0 percentage up to 100%. Okay, so we will look at the addition or increasing of composition in terms of percentage. Okay, so and then we have a definition in terms of system, equilibrium related to the free energy, and also phase equilibrium. Okay, and then we have a phase diagram. Already mentioned to you that phase diagram, that there are a lot of information can be gathered from the phase diagram. So in this case, we have a copper nickel phase diagram. Okay, and at y-axis we have a temperature. We varies the temperature, or we increase the temperature, or we look at the temperature decrease during the cooling process. Okay, starting from the highest or the molten composition of element. Okay, starting to cooling down, and what will happen during this process. Okay, so and then we have the x-axis. You can see there is a different in terms of percentage. If we look at this phase diagram, which is copper nickel phase diagram, which is nickel will be increase in terms of percentage, starting from 0% up to how many percent that the phase diagram show to you. Okay, in this case, we can see it up to 60%. Okay, so in phase diagram, so we will see what will happen during the percentage of when we increase the nickel up to, in this case, if we have this line, around 35%. So what will happen when we increase, when we set 35% of nickel in copper? Okay, so during the solidification process, what will happen to the composition or the phase? Okay, composition. Okay, so from there we will need to analyze, or we can get the information in terms of the prediction, okay, in terms of the understanding of the what will happen during the cooling process, okay. And also we will see the phase diagram of the basic phase diagram of water or H2O, whereby we see the existing of solid, which is ice, existing of liquid, which is water, and the existing of the gas. Okay, so during the process, we will see what will happen when we increase the pressure, okay, and at a certain temperature. Okay, along the way, there is a phase transformation takes place. And if we see from the vertical line starting from number 1 until point number 5, there is a phase transformation starting from gas, vapor, and then transform to solid, and also finally to liquid at point number 5. And also happen to the horizontal, whereby we have point number 6 and until point number 9. You can see the transformation takes place during the process at 1 atm. Okay, whereby when we increase the temperature starting from negative something at 0.6 and up to something degree Celsius, and we can see the phase transformation takes place from solid, liquid, and finally gas. Okay, so this is the basic phase transformation of H2O. So we can try to explain what will happen during that line of x-axis we set, or during the y-axis we set. Okay, so it also happened to the phase diagram to other materials, composition, binary phase diagram. Okay, and also other. Okay, so in this case we will mainly discuss on the binary phase diagram, okay, related to the two composition of element. Okay, so after this we will see several two component involved. Okay, so a lot of material combination. Okay, so that we will see and we will analyze what will happen during the process in terms of composition, how many percent of liquid, how many percent of solid, or combination of liquid and solid in the region. Also, we will look at the percentage. Also, we look at the composition and also the microscopic, okay, of the phase axis. Okay, so and then we also learn how to construct a phase diagram. Actually, the construction of phase diagram involved with the quite tedious process. Okay, actually the process is we will set the composition first. Let's say we combine 2% starting from 0% of material or foreign element, and then look at the changes of the temperature, and then we will look at the solidification start and solidification end. Okay, and finally we will look at the various line, and then we can overlap and construct the phase diagram. Okay, so in this case there is a phase diagram complete set. If you can see, there is a different of composition starting from 0%, okay, of nickel, and then up to 100%. And during the process of the combination, at a certain combination percentage, we can see there is a starting to solidification start and finish. Okay, in this case we can see this copper nickel phase diagram. There is a existing of liquid and solid at the same time. Okay, so in this case we can see the construction produced here. We can name it as a liquidus line and also the solidus line here. So, and then we have the liquidus area, whereby this is the liquid area, whereby this is the existing of liquid composition in terms of nickel and copper. Okay, and during the solidification takes place, there is a transformation, the coexisting of liquid and solid in this area. So, and then at the lower temperature, we can see there is a 100% of solid takes place. Okay, so in this case, we can analyze, we can determine the boundary of the liquid and solid, the boundary between the interface of liquid solid. Okay, so from there, the construction finish, we look from the various of nickel starting from 0% up to 100%. So from there, we can set the look at the projection or prediction, whereby we can put a varies of line. Let's say we want to look at the 40% of nickel in this line, what will happen during the solidification. Okay. So, and then we come across the Liver rules, whereby in the Liver rules, we can get the information of the composition, phase composition. Okay, whereby if we have set somewhere a point somewhere around here at B. Okay, so from there we can set at B position. We know there is a condition of phase whereby we have alpha and liquid condition. So from there we need to determine the composition. Okay, in this case we need to draw a tie line here. Okay, whereby the tie line is a horizontal line of the value of this temperature, say somewhere around here, so we can determine the temperature here. So from there we make a horizontal line and then intersect at this liquidus line and also intersect at this solidus line. And then we make a projection to the x-axis to make it a projection of C alpha and also C liquid here. So from there we can determine the value of C alpha, which is you can make a approximate, and also from we can get the value of C liquid as somewhere around here. Okay, so in this case from the Liver rules, okay, to determine the fraction of in terms of percentage of existing of this at this point we have the intersection of liquidus line and also intersection of solidus line. So here the existing in this area is in terms of liquid and also alpha. So we need to determine the fraction percentage of alpha and liquid here. So in this case, we can use the Liver rule, whereby use the formula to determine the fraction in percentage of composition. So previously, at the end of my lecture, I already give to you the point. So you to determine the value of point B here and also point C here. So here is the discussion how to get the value of point B, whereby we know that at point B there is existing of alpha and liquid. So at point B, we need to draw a tie line here to indicate the cross section at point here at solidus line and also the solidus line here. So here and then we make a projection to the x-axis to determine the composition of alpha and also composition of liquid here. So here you can make a guess or approximate of the value of C alpha and CL. Okay, in this case, we need to determine at this point, we make an approximate at point B is happen at the temperature of 1225. Okay. So in this case, at point B, we apply the river rules. So to get the value of C alpha, C liquid, and CO, from there we can get the CO is 30%, and also C alpha and CL, which indicate 35% and 25%. Okay, in order to get the fraction of percentage in alpha phase fraction and liquid phase fraction, so we apply the river rule formula, whereby we have 35 minus 30. So 35 is supposed to be in C alpha, okay, minus 30, this range, okay, and then we divide the total range from here and from here. So that means we have 50% of alpha phase, and also we get the 50% of liquid phase. Okay, this one is approximate, so maybe you set the different value from others, so it doesn't matter, at least we can calculate the value by using the river rules. Okay, so what will happen to the at point C, also the same thing we will use. From there we need to determine the temperature and also the composition C alpha and CO and CL. So in this case, at point C, we have the value of C alpha, CO and CL, which is 50% C alpha, CO 45%, and CL 37%. So in this case, to get the value of percentage of alpha phase, we get the value of 38%. Okay, and liquid phase, we get the value of 62%. So we will get at point B, just now we will see the amount is 50-50, and at point C, we can see the amount is for the liquid percent is less if compared to the solid. Okay, solid alpha fraction is less if compared to the liquid phase, which is 62%. Okay, so this kind of information to get the composition and also to get the percentage is very crucial in the analysis after this. Okay, you need to understand this in order to analyze the in phase diagram what will happen at the certain line that we project. Okay, so the question can be set in many ways, so that from here in part A, we just learn about to get the by using the Liber rules to get the value of fraction of alpha phase and liquid phase. So after this, we will see you need able to draw a microscopic of the existence of alpha phase and liquid phase at the certain point. Okay. So this is the recap of the part A. So and for the part B, we will go for the Gibbs phase rules. So there is another rules. There is a formula to get involved with related to the parameter connection with the composition. Okay, and also after this we will see. And this one is the end of the construction of phase diagram, part B. So, and then we will go to analyze the different phase diagram at a certain point, okay, at a certain line, horizontal and vertical line. Okay, so for the Gibbs phase rule is basically dedicated by the in the thermodynamic law of thermodynamic. And this one is represent the criteria for the number of phase that will coexist with the system at equilibrium. In this case, we have the formula whereby the formula will link effect each other in terms of the existing of composition related to the parameter such as temperature, such as composition. Okay, so in this case, we will see the equation whereby we have P plus F is equal to C plus N, by the P is a number of phase present. So we have the one phase, two phase, three phase present. Okay, so after this we will see what is different between one phase, two phase, and three phase present. And also F indicates the degree of freedom. So this one is represent the parameter that involved in the phase diagram, which is temperature, pressure, and composition. Okay. So how many? In this case, if we have a three parameter involved, can put it as a 3. Okay. So if the involved in which is temperature only, we will put the number is 1. Okay. So and then we have C. C indicate the component in the system. Okay. Basically, during the lecture, we will involve with the binary phase diagram only, whereby the only two component involved. In this case, for the two component involved, the C value is 2. Okay. And then we have N is the non-compositional variable. Okay, that one is basically related to the temperature and pressure. Okay, so for example, okay, we have for the binary temperature composition phase diagram. So for example, we have the copper and silver phase diagram. Okay, from there we can see what will happen to the Gibbs phase rule in terms of PFCN. Okay, the parameter involved here is let's say we have the only temperature involved, so we indicate the value of N is 1. So let's say we have the component because of involved with two element, which is copper and silver. So we indicate the value of C only, which is 2. So we have in the Gibbs phase rule, we have 4 involved, 4 term involved, which is P, F, C, N. So it will asking for the value of maybe to get the value of P, or to get the value of F or something. So in this condition, we need in order to get this value, we need 3 value first. Okay, so in order to get a value of F, so we need to have the information of 3 other value, which is P, C, and N. Okay, otherwise we cannot get the value of F. Okay, in this case, given the N is 1, given C is 2, and given phase present P is 1. Okay, in this case, the phase present is consider the single phase only, which is in the phase diagram only condition of phase exists is only alpha, beta, and liquid. Okay, this one is a single phase, they call it. So if the phase diagram consists of the combination of alpha and liquid, there is another phase. Okay, after this we will see. Okay, so let's say the P is number 1. So from there we can get the value of F. Okay, by substitute the value of N, C, and P. So finally we will get the value of F is equal to number 2. Okay, the 2 is indicate the value of control variable. Okay, we know that this control variable for indicates the F. So we know that the parameter are the composition and temperature. So let's say if we have the two phase coexist, in this case the actual two phase coexist, that means we have the alpha liquid, beta liquid, and alpha beta. This is a two phase exist. So that means the value of P is supposed to be number 2. Okay, so the P is equal to 2. Okay, in this case, if we have the P equal to 2, so what happened to the F? The F value is equal to 1. Okay, after we substitute the value. So this is the table that indicates the difference between value of P. Okay, start from number 1. Okay, the P, which is indicate the single phase or two phase exists or three phase exists. Okay, in this case, for the single phase, we will see the phase diagram whereby the only existing of alpha, beta, and L region. So for the two phase coexist, we will have this kind of phase, which is alpha and liquid, beta liquid, and alpha beta. Okay, and other three phase involved. Okay, so in this case, we have P equal to 1, P equal to 2, P equal to 3. What will happen to F? The F value will varies, which is F equal to 2, F equal to 3, and F equal to 1, F equal to 0. So what is the meaning of F equal to 2? Okay, which indicate the composition parameter involved, which is the composition and temperature. Okay, for the F equal to 1, we will indicate the whether we don't know whether the composition or temperature. We need to specify from the, okay. So, and the final one is the composition of all three phases and temperature are fixed. Okay. So, for the Gibbs phase rule, okay, in the in this slide, we show you the P is equal to 3. So, what will happen to the F value? So the F equal to 0. So this one indicates that the meaning of the composition of all three phases and temperature are fixed. Okay, in this case, the meaning of this, if you can see, there is a line here. Okay, the line indicate the temperature is the same. Along the way, we can see different in terms of phase, the presence of phase at this point B. Okay, and then at point E, okay, and also at points G. Okay, we can see this condition meet for a eutectic system by the eutectic isotherm. This one is a term that we use at the certain point that the liquid, okay, we can see there is a point whereby we call it the eutectic point here or eutectic temperature along the way. So at this point, the transformation from the liquid and then to the solid, okay, at this composition, if we project along the axis, we can see there is the composition of the Ag here. So from this point at point E, the transformation takes place whereby at the higher level of this temperature at this point, whereby this is the liquid phase, and can see at this point there is a borderline of liquid and solid. Okay, so this is, we call it the eutectic transformation takes place along the way. Okay, and we call it a eutectic point or eutectic temperature along the way. Okay, at 779 degrees Celsius. Okay, so at this point we can get the value of alpha here. Okay, whereby the value of alpha phase is 8% of Ag, and we can get the value of liquid here at this point which is 71.9%. Okay, the percent we can get from the projection at axis here. And also along this line of temperature, we have another one which is the existing of beta. Okay, the beta area here is the 100. This one is percentage of existing of only Ag. Okay, only Ag. So this area, if we look at this point is alpha, this is where the area of the existing of alpha only. Okay, so along the way there is a phase transformation. Okay, and finally we can see the existing of Ag only because of the Ag composition is high. From there we can project the composition along the line at the temperature set. Okay, whereby from there we will get this is due to the P is equal to 3, and finally we get the F value is equal to 0. This is the meaning of this F equal to 0. Okay, whereby the line is here. Okay, so from there we need to apply the from lever rules. Okay, and then to calculate the value of the composition, and also we can get the in terms of percentage. So here we will try to analyze more details on the line of projection that we set. Okay, so please consider the copper nickel system. In this case, we have the copper nickel phase diagram, and we look at the various of nickel along the way up to 60%. Okay, so from there we can see when we set the what will happen at the area of the point or the at 1300 degrees Celsius at 35 nickel, and or the rest is 65 copper. Okay, or we can see the line here. Okay, up to this point. Okay, what will happen in term of the composition and also the microstructure. Okay, so that we can draw the microstructure at that point. Okay, so in order to understand it, at point A, we have 1300 degrees Celsius, and from there we can see this is where the area of liquid, okay, phase. So we can say that this area is a liquid alloy. And what is the composition in this point? We have the liquid of the existing of 35% of nickel. Okay. So for the microstructure, we can draw is something like this, whereby only liquid at 35% of nickel. Okay. So what happened to point B? The point B is in the intersection of the vertical line and the liquidus line. So at point B, okay, at this point, at a certain temperature, which is whereby the temperature is around 1260 degrees Celsius, so we can make a tie line, which is the projection of this line. We can see there is a 2 point at this temperature. We have the intersection is at point B, and also the intersection at this point. Okay, the intersection at point B, we have the alpha, the liquid phase, and also at this point we have the alpha phase point. So this one we have a two composition. Okay, whereby the composition at alpha, the value is 46 nickel. Okay, whereby the value is here. So, and also can make a short form is something like alpha 46 nickel is something like this. So after this we will use this kind of term. okay, indicates that the existing of alpha phase at 46% of nickel. Okay, so and at point B, whereby we have the intersection of horizontal and liquidous line here, this consists of liquid. Okay, we can put it as a L in bracket is 35 nickel. Okay, so this one is a fraction of alpha phase. We see that the fraction of alpha phase is increased. Okay, from 2 to 46. Okay, so and for the liquid phase is the same as 35 if compared to this at point A. Okay, so from there at point B, we need to make a tie line to get the value of alpha phase and also the liquid phase. Okay, and what will happen when we increase to the at point C, okay, at 1250. Okay, before that, at point B, we can see in terms of microscopic structure, we can see there is a starting to nucleation takes place of the alpha phase, okay, whereby the alpha is at the 45% of nickel. Okay, at that point is the alpha is start to nucleate and start to solidify. Okay, and if you can see at point C, whereby we have 1250 degrees Celsius, we have the value of projection when we set the tie line here, we have this point at liquid, and also we have the alpha here. So we need to determine the value of liquid and alpha composition by make a projection. Okay, at along to the x-axis. Okay, in this case we have the alpha and liquid is 43 and 32. Okay, we can see the liquid here along the way. You can see there is a slightly reduce of the value. Okay, so if you can see from the microscopic point of view at point C, we can see the nucleation is take place and it's become more bigger and bigger. Okay, so you will be able to draw the diagram is something like this. So at point D, the cross-section line of horizontal and the solidus line at point D. Okay, and then we need to project the horizontal line at this point. Okay, and then we can get the value of alpha, which is 35, and also the L speed at 24. Okay, here. So along the way at D, we can see there is a complete solidification. There is a in this point there is a borderline. Okay, and we can write down is something like this. And for the complete solidification, maybe lowest area here. Okay, from there we can get the value of solidification takes place, and we can say there is a 100% solidified, whereby the alpha value is 35. Okay, that one we call it polycrystal solid solution. So from there we can draw the solidification 100% of alpha is something like this. Okay, so from the projection from the at 35% of nickel, so this line will be able to draw in terms of microscopic diagram starting from point A up to point E during the solidification process or the cooling process.
Excuse me, doctor. Sorry to interrupt, but
Yeah.
I have a question. What does WT percent means from the graph just now?
Weight percentage.
Oh.
Previously, I already explained that WT is weight percent.
I see. Okay. Thank you, doctor.
So for the, let's say other phase diagram, we need to consider is a plumbum and tin. Okay, here plumbum and tin, and also copper and zinc. This one is a binary phase diagram related to the application of solder. Okay, this one is we can classify as a soft solder and hard solder. For the soft solder is a plumbum and tin, and for the hard solder is copper and zinc. This one applied for the various application in term of the lead, okay, plumbum or tin, have apply for the soldering application for the electrical wiring, soldering, and for the copper zinc applied application in term of the decoration they use for the make application in term of appearance like a drawer, pulls, and doorknob, and other application like lock, hinge, gear, zip, electrical plug, and socket. Okay, so this kind of binary phase diagram of soft solder and hard solder. Okay, we can see diagram is something like this. Okay, so previously we are already look at this kind of phase diagram. In terms of copper and zinc, there is a more complicated phase diagram involved. Okay, so after this we will see only this phase diagram, and we try to analyze this kind of phase diagram. Okay. So this kind of lead tin phase diagram or PBSN phase diagram, we call it binary eutectic phase diagram. This one is very special because of we have the term of eutectic, and previously you already I already mentioned about the eutectic, whereby the eutectic is where we have the transformation phase occur at this line. Okay, this line. Okay, this is one is quite special because of the liquid will transform along this line to the alpha plus beta. Okay, so the alpha indicate for the PB, the beta indicate for the SN. Okay, so in this case, from there we need to try to analyze what the region involved in the phase. Okay, for the binary eutectic phase diagram is quite a simple phase diagram involved. Okay, so we have they call it binary eutectic phase diagram due to this line here. Okay, at this point. Okay, if we compare to other line, let's say we have this line. Okay, the liquid also happen during the process of solidification. Also, there is a existing of alpha and L in this area, and also the alpha and beta in this area. Okay, but in this case of point E, there is a liquid and then jump to the alpha and beta. Okay, so and then the interesting part of this phase diagram, we have three single phase region. Okay, three single phase region. That's mean we have this region. Okay, we have alpha region, which is number one region, and then we have the number two region. Okay, this one is a single phase. Single phase. Okay, single phase beta. We have single phase alpha, and then we have single phase liquid. Okay, so these three, we have a three single phase region. Okay, alpha, beta, and liquid. And the second two phase region, we have the alpha liquid, and then we have beta liquid, and then we have alpha beta. Okay, so there is a two phase region. try to analyze from this phase diagram, from the line that produced, which is for the alpha phase, we have the borderline is alpha, the borderline is A to B here, and also to C here. So this is where the region of alpha phase. Okay, this region we consider as a pure lead. Okay, because of no mixture with other. Okay, in this area we have the mixture of liquid. Okay, and also this area is mixture of beta. Okay, in this case we have the consider as the pure lead. Okay, and then this is a solid solution. Okay, solid area. And then for the tin, okay, at the solid composition. Okay, for the line here, maybe for the line here, we have the composition of the soluble of the existing in tin. Okay, so for the beta phase, this is in this color beta phase. For the beta phase, we have this area is the solid solution risk of SN. Okay, and then is considered the pure SN or tin. And then PB lead as a solute. Okay, so this is the information we can gather for the line of AE and EF. This one AE and EF here. So this line is considered is liquidous line, and for the solidus line, the line is AB. Okay. Okay, solidus line is AB here. FG. Like this line. G. And also.
Excuse me, doctor. Sorry to interrupt, but I have a question. Dekat the alpha phase, when it says solid solution, what does it mean? Like, how can a solution be solid?
The solution is the term previously we already explained about the considered as a solution in solid. Okay, so that's mean there is a this one is also the borderline, which is the mix. Okay, in borderline is a mixture of other element. In this case, we have the SN. So the solid, in terms of solid solution. Okay, so because of the mixing of these two, we call it a solution in the term of solid. Okay, so this one is a solid. Okay.
Oh, I see. Okay, thank you, doctor.
Right. So because of the existing of the two element, okay, we set the solution. Okay, so there is a liquid solution, there is a solid solution. Okay, okay, for the comparison. Okay, in this case we have the line of BEG. So it's also, we call it a solidus line. There is a three line in this case, AB, DEG, and also FG. There is a, we call it solidus line. Okay, and also another, this is new term for you because previously you already learned about liquidus and solidus. This one is we have solvus line. Solvus line is whereby we have BC and also this line. Okay, GH. Okay, this one is a solvus line. Okay, the transition, the borderline between alpha, between the solid and also the existing of two alpha and solid, solid of alpha beta. Okay, right. So the solubility limit of alpha phase. Okay, so we can see the limit here. So the solubility limit here for the alpha phase, we can see at this point, at this line, on also at this line. Okay, BC. Okay, the maximum solubility of SN in PB, okay, is 19.2 point here. the maximum. Okay, so we call it the highest limit of the SN, okay, to be in the soluble because of the borderline. Okay, after this there is no SN in this area. Okay, only 100% of alpha or 100% of. Okay, so this point at B is the borderline or the maximum line existing of the SN, which is the value is 19.2. Okay, if the value of 19.1 percent, that's mean there is no there is no of SN. Okay, in this part, okay, whereby we can see the 100% of alpha. Okay, which at this point is the temperature is 183 degrees Celsius. Okay, so we can see when we try to look at the projection of the line. Okay, let's say we have the 10% of alpha, 10% of SN. Okay, we put 10% of SN during the solidification, or we can see the line here. Okay, the line projection during the cooling process or solidification process. Okay, the existing of liquid, and then we can see the existing of alpha and also the existing of alpha and beta. Okay, after this we will see the microscopic point of view what will happen to this area. Okay, and also along the dedicated area of this. Okay, at the slope of BC, okay, you can see there is a solubility of SN in PB. Okay, here this slope. We can see during the process of the temperature decrease, okay, SN become less soluble in PB. Okay, so this is the line. So and then we have a solubility limit of beta. Okay, we can see from this point, okay, at 97.5. Okay, so in this line we have this slope which is considered at point GH here. Okay, at this point the solubility of PB in SN decrease with temperature. Okay, when the temperature increase, the solubility of PB, so PB is become lesser. Okay, and the SN is become higher at okay, at this point. So and then we have the point liquidus point at AEFE. Okay, at this point line, you can see at this line. Okay, so this line we can see at this point. Can say there is a eutectic reaction takes place at point E, whereby the liquid we will transform to the alpha and solid solution here along the way, whereby it not transform to the alpha liquid, okay, or other beta liquid here. So in this case, we can see there is a transformation takes place along the way. Okay, the phase of alpha liquid and beta liquid is not happen in this at this point. Okay. Okay, this is where we call it point E is a eutectic point, or the temperature happen at this area is 183 degrees Celsius, whereby this temperature we call it eutectic temperature. Okay. So we try to analyze at different vertical line or different composition. Okay, in this case, we try to look at the C4 here, line C4. Okay, what will happen at point different point. Okay, and we will start during the solidification at point J. Okay, whereby here we know that this area is a liquid area, whereby the composition of liquid which consists of the we have the 40% of SN. Okay, So this one is totally liquid. We have during the process of the solidification, we will start to look at the different point. Okay, what happened at point K? Okay, this area is a borderline of liquid and alpha liquid. Okay, and then this area is a borderline is alpha liquid and also alpha beta. Okay, and then we can see that what happened at point K, which is the alpha phase continue to grow. Okay, we can show the microscopic diagram is something like this. And then we can see the nucleation takes place of the alpha. Okay, and can see blue color here. And then the composition at point L, the point L whereby the value is higher, a little bit higher temperature. Okay, so what happened to this area? Okay, okay, at this area, at this point we can see let's consider the point whereby is a little bit higher at 183, maybe 184 is something. So at this point we can see it at the eutectic temperature. At this point, we can project the composition. Okay, at this area, we can see it's slightly higher temperature at 183, maybe 184 or 183.5 or something. Okay, from there we can make a tie line here to project at horizontal line. Okay, we can see we make a projection horizontal. We have 2 points here at point B and point E. Okay, at point B we have the beta, alpha point. The value is 19.2, and at point E we have the different phase of the liquid phase of point E, which is the value of 61.9 here. So at the value of at point L, we need to use lever rules to get the value of point B and E in terms of composition, if required for us to get the value. At point K also we can get the value, which is the composition. We need to make a tie line here. Okay, but in this case we don't have any value, so maybe we can just make an approximate value here, maybe less than 19.2. Okay, in this area maybe 18 or 17. Okay, for the alpha, and maybe at this area for the liquid. Okay, we have the maybe 40, 45 or something like that. Okay, so at point K and point L also can determine the composition. Okay, in case of point L is higher a little bit from the 183, we can take the value of 19.2 for the alpha, and also for the liquid have the 61.9. Okay. Okay, at point M is the value is a little bit lower than value of 183 degrees Celsius, maybe 182.5 something. So at this area, okay, we can see there is a different in terms of microscopic, and also the value of alpha, and this one is existing of the phase which is the alpha and plus also eutectic structure. Okay, whereby here the structure a little bit different if compared to this point L, whereby if we can see at point L we have the nucleation is start bigger and bigger of alpha, and at point M there is a kind of something like this. Okay, whereby we can see we can see a structure of eutectic takes place. whereby here we have the existing of alpha and beta. If you can see a microstructure is something like this. Okay, so in this case we have the blue color is alpha, and also the red color is beta. Okay, the existing is something like this. Okay, so and also we can see there is the circle bigger area, and also the lamella structure happen here. So and then we have the we call it the static alpha. Okay, the value is 19.2. We can get the value is at this point. Okay, and also we have the beta value is from here. Okay, so this is the value of the beta 97.5. Okay, so for the temperature is lower than 183 degrees Celsius, a bit lower. So the 2 point we need to take is point B, at point B, and at point G. Okay, the point if the position is higher a little bit at 183, we need to take at point B and at point E. Okay, so this is where we can get the composition. Okay, at the actual reality of the composition of PB and SN at this point, actually we can see something like this, whereby we have the darker color of round area, okay, whereby the existing of alpha, eutectic alpha, okay, you can see dark color, and then the white color is existing of beta. Okay, okay, so this one indicate the composition of PB and SN at the 40% of SN. Okay. Okay, what happened if we look at this line? Okay, so whereby we have the eutectic line here. Okay, what happened at point H? What happened at point below than 183? So we need to consider. So this one is they call it a eutectic line or eutectic composition, whereby it's happened at 61.9% of PSN. Okay, let's see, consider at point H. The point H, we already know that this is the liquid area. So we have those at this point, we nothing to draw, okay, something like this. And then we have at point I, whereby is lower than 183 degrees Celsius. This point, we have the transformation from the liquid, and then we have the transformation of existing of alpha and beta. Okay, and we can see a lamella sandwich between the alpha and beta. Okay, this value, okay, let's consider this value is a little bit lower than 183 degrees Celsius, maybe 182.5 degrees Celsius. Okay, in order to take the composition of alpha and beta, we will try to consider at this point. Straight away take the value of 19.2 of alpha, and also 97.5 the value of beta. Okay, composition of alpha and beta is something like this. Okay, we can write of the blue color is alpha and red color is beta. Okay. So from the reality, from the diagram, we'll see from the scanning electron microscope is something like this, like kind of lamella stripe. Okay. So if we try make a deeper analysis along the way of this region alpha beta region, okay, we have this region whereby before this line, okay, before this line, and this line, and also after this line, okay, we can see slightly different in terms of composition of the alpha and beta. Okay, in this line we can divide into three parts. The first part is the area before this line. We call it hypoeutectic. Okay, this line we call it hypoeutectic. This borderline we call it eutectic, and after this line, this area we call it hypereutectic. Okay, so if you look at the diagram, you can see quite a different in terms of the round area of alpha, and this one is a round area of beta. Okay, so the rest is a little bit the same. Okay, at this line, we call it eutectic line. There is no existing of round. Okay, so this is the borderline. Okay, during the transition. Okay, and what happened at the other line at the area of the around 2 to 300 400 degrees Celsius. Okay, we try to look to consider at the line of C1 here. Okay, in here we can see a different of point A, point B, and point C. Okay, here we can see there is at point A is 100% of liquid, and at point B whereby the alpha is start to nucleation takes place, and the microstructure is something like this, and at point C whereby this is the alpha region, which is 100% of alpha. Okay. And also if we have this line, okay, we can see there is a slightly different of the alpha and also beta takes place. Okay, so I think you would be able to draw is something like this. Okay, at a line of C2. Right, and then finally, we will go for the previously we have eutectic, and this one we have the peritectic. Okay, the peritectic also happen in the different phase diagram. We have the PTAG phase diagram. Okay, if you have the PBSN phase diagram, only we can observe the eutectic. For the PTAG phase diagram, we have the peritectic. Okay, the peritectic happen when we see at this point. Okay, we have the transformation of the alpha liquid to the beta. Okay, here you can see from the alpha liquid to the beta, alpha liquid to the beta. Okay, whereby the alpha is not existing in the beta due to the surrounding of the beta encapsulate of the alpha here. Okay, this one we call it the peritectic phase diagram happen at this area of the phase diagram of the PTAG. Okay, so the peritectic transformation takes place in two phase interact at the fixed temperature, whereby the temperature along the 1186 degrees Celsius. Okay, here. Okay, the peri means the around that the original solid phase becomes surrounded or coated by the new phase. Okay, so the final at this point we'll see the 100% of beta. So the alpha is no longer exists at the point whereby the beta is surrounded. The alpha is surrounded by beta and finally vanish. Okay, along the way. Okay, this is we call it the peritectic line or peritectic composition at the 1186 degrees Celsius. That temperature we call it peritectic temperature. Okay, so from there let's analyze what will happen at when we introduce 25% of Ag. Okay, along the line, maybe we can try to draw a microscopic diagram here. Okay, what will happen when we see at 42.4 percentage of Ag. Okay, whereby at this line we can see the line hit at the point. This composition, we call it a paritetic composition at the line of temperature 1180. Okay, and also what happened when we introduce 55% Ag along the way, we during the solidification is experience a lot of phase transformation along the way. Okay, and also try to draw. Okay, in this case we have two line here, alloy number 1 at composition of 42.4 and alloy number 2 at the composition. How to get the value of the percentage of phase fraction. Okay, so in this case let's consider at this alloy number 1. Okay, so what will happen at the temperature of 1400? Okay, at this line we need to make it a tie line here. Okay, at this line, so we have two intersection point here and also at this intersection point here. So we have the alpha point here and also the L point here. So the value we need to make a intersection at, make a projection and intersection at y-axis, and then we get the value. In this case, the value already given. The alpha composition is 7. The liquid composition is 55. So in order to get the fraction of alpha and fraction of liquid, so we need to apply the Lever rules and we get the value. Okay. Okay, in this case we have 26% of alpha phase, and we have the rest is 70% is for the phase liquid phase. Okay, once you get the value 26, the rest is 74. So it will make up total is 100%. Okay, and what will happen at the line of 1185 here, 1186. Okay, this one is a point whereby the value is higher, a little bit higher value, maybe 1186.5. Okay, so at this higher value, we will make a tie line here. When we get hit this line 10.5 and also hit this point 60.3. Okay, here. So we make a calculation by using Lever rule to get the percentage. Okay, here. So, and what happened when the line is below then 1186? Okay, maybe 1185.5. So we will make a tie line to project and we hit this point 10.5 and also this point. Okay, 42.4. So from there we can get the value of percentage. Okay, at this point, whereby the only the existing of beta only at this area. So the alpha, the liquid phase is no longer. Okay, so this point we have only a beta phase. Okay. So what will happen at this point? So this line, maybe you can make it by yourself. So I think we at the end of the lecture, and what will happen at this line of 55 Ag, percent Ag. Okay, and okay, this one maybe you can go through to get the value. Maybe I have some mistake from here. Maybe you can work out to get the value. Okay, what happened at the 45%? What happened to the 60%? Maybe you can draw the microscopic value. Okay, microscopic diagram, sorry, bukan microscopic value, microscopic diagram, and also to calculate the value of the fraction by using your Lever rules. Okay, to us. Okay, before we stop.
Excuse me, doctor, I have a question. Can I look at the eutectic diagram just now? Doctor, I want to ask, kenapa for the alpha it's 19.2 weight percent for SN, but for the L liquid it's 61.9%?
At point M.
At point L. Macam mana
Yes.
macam mana nak dapat value 19.2% tu dengan 61.9, because at the line tu isn't it like 40%?
At 40% this line.
Yes.
This line, if
Mhm.
this line is 183 degrees Celsius, betul-betul atas line ni, we will get memang 19.2 dengan 61.9 lah, kan? This line. Because this line is if you consider the value of the upper, kalau upper value 183 183.5 upper sikit je saja, we can get the value mungkin dekat atas ni lah, dekat sini. Okay, dia ada intersection between alpha liquid dengan liquid kat sini.
Oh, I see.
Dia atas sikit dia. Dia bukannya betul-betul point 61.9 ni. Okay. Dia atas sikit. Mungkin kalau kita projection ke bawah ni, dia punya line dia, point dia dekat sini mungkin 61. Mungkin macam tu lah. Okay. Kalau kita besarkan point ni, kalau kita besarkan point ni. Point ni besar kan. Okay, kat sini. Dia mungkin duduk atas sikit kat sini lah. Dia bukan betul-betul 61. Dia duduk kat sini. Atas sikit. The value dia kalau buat projection at at axis tu, mungkin dia value dia 61.5 macam tu. Sikit je. Kalau awak ambil baris, buat garisan lah. Buat projection lah. Okay, tapi kita tak tahulah point tu berapa. Tapi at this point, easy to explain. Just take a value atas sikit je, maybe at 183.5 degree Celsius macam tu. Atas sikit value, we can get the value maybe 61.5, 61 ke value dia macam tu. To make it easy, we just take 61.9 lah macam tu. Okay. Dia ada plus minus macam tu. Okay.
Because faham, tapi saya a bit confused dekat yang dotted line tu, doktor. Kan dia menuju kepada 40% kan? So 40% tu sebenarnya menunjukkan apa?
40% tu if the point is here, okay. The composition bila kita apa ni? When we put 40% value of SN, okay, 40% of SN, 40% of SN itu akan behave different microscopic punya diagram. Kalau kita heat at a certain temperature, when we heat, we start to cool different set to heat and set to cooling process lah. Okay.
Okay.
Along the way tu, okay, kalau kita tengok dekat sini, in term of microscopic diagram, kita akan nampak macam ni lah. Satu yang dekat sini liquid ni, then they start nucleation macam yang kita belajar sebelum ni. Yang ni dah detail lah. Start nucleation, it will have solid start to nucleate lah, and then bigger and bigger kat sini. Kita nampak yang dekat sini ya. Ni ya, start bigger and bigger. Yang sebelum ni kita tengok untuk satu material saja. Okay, macam kita ada copper, liquid copper, molten copper, kita start to cooling, start to solidify. Okay, kita tengok satu. Tapi sekarang ni untuk yang satu tu copper sajalah, start to nucleate and bigger grain boundary apa semua tu lah start. Okay. Tapi this one and this one is depend on the alpha and beta kat sini sebab ada dua. Okay, this area 40% alpha start to nucleate kat sini. Kalau you ambil dekat sini, area sini, line ni. Line ni, kalau you tengok dekat line sini, Line sini alpha dah tak start nucleate, dekat sini beta start to nucleate lah, kat sini. Line ni sampai bawah ni. Okay, jadi kalau dekat sini saya ambil line sini, saya garis satu line sini, kalau ada point dekat sini, gambar rajah dia mungkin sama macam ni juga, tapi yang biru tu dah jadi merah lah kat sini. Dah jadi beta. Okay, line sini alpha dengan liquid saja exist. Sekarang ini beta tak ada. Okay, beta tak ada. Sungguh pun ada beta. Sungguh pun kita introduce beta tu 40%. But this area beta no longer exists because of the nucleation is not takes place lah. Beta ada, tapi in the liquid form lah. Okay, alpha in the solid form kat sini, beta liquid form. Okay, so alpha and beta mix together, liquid pun ada, alpha pun ada, and then solid alpha start to nucleate lah macam ni. Okay, so and then we have the L liquid ni dalam bentuk solution lah, liquid dia ada alpha ada beta dalam ni. Okay, liquid dalam bentuk liquid SN dengan liquid PB. Okay, alpha ni dah memang spesifik untuk solid lah, solid. Okay. Along the way masuk turun ke bawah dia start dia jadi besar kat sini. Okay, and then bila start saja transition ke bawah ini, dia dah ada beta dah kat sini. Okay, dia dah start ada beta. Okay, beta ni dia start ada, along the way ni dah solid terus lah. Alpha dengan beta, dia tak ada dah liquid kat sini. Okay, dia jadi macam ni ya. Macam ni.
Bila dia sejuk, doktor dia ada alpha and beta ya, doktor?
Dia dah keras lah, dia tak ada liquid lah kat situ. Bila dia start liquid tak ada kat sini, dia dah start keras lah kat sini. Dia form dalam bentuk macam ni. Lamella dengan ada bulat-bulat kat sini. Yang ni dia special sikit. Kalau dekat area sini, area region sebelum boundary dekat E ni, dia ada bulat-bulat dekat sini ya. Dia bulat-bulat ni. Kan kita ada hypo-eutectic dengan hyper-eutectic kan, dekat situ. Kalau awak tengok yang pergi. Tengok yang ni. Kalau tengok yang ni, dia ada 3 region. Satu region sebelum line ni. Lepas tu kita ada line. And then kita ada satu lagi region sini, ada 3 region. Satu hypo-eutectic ni, eutectic dengan hyper-eutectic. Kalau hypo-eutectic, kita ada bulat-bulat sama juga macam hyper-eutectic, tapi yang ini consist of alpha.
Yang hyper tu, yang besar-besar tu represent beta lah, yang B tu.
Sebab region sini region beta ni, region beta ni. Sebab kat sini daripada liquid solution, lepas tu dia transform jadi beta dengan liquid, lepas tu jadi beta saja. Beta dengan alpha lah kat sini. Tapi dalam sini ada beta bulat lah. Dia punya structure properties dia macam tu.
I see. Okay, thank you doctor. I understand better now.
Okay,
Okay,
so
thank you, doctor.
okay, sama-sama.